Good day once again. I'm going to present on the time value of money. This is a tutorial that introduces us to computations that include interest rates. So the objectives are to show how interest rates may be expressed in different time periods. That is, describe the relationship between the rates of interest and discount over one effective period arithmetically and by general reasoning. Then describe how to take into account the time value of money using the concept of compound interest and discounting. That would include accumulate a single investment at a constant rate of interest under the operation of simple and compound interest, define the present value of a future payment, discount a single investment under the operation of a simple discount at a constant rate of discount. As an introduction, we'll define the terms. Interest is the first term, is the reward paid by the borrower for the use of an asset which is capital which belongs to some other person of or organization, the lender. So the borrower requests for an asset from the lender, which is called capital, and then they have to pay interest as a reward to the lender for giving them money. And capital is also called principal, which means the principal that the borrower receives plus the interest they have to pay is equal to the accumulated value that the lender receives. And if you borrow 100 from a bank and you have to pay back 120 in 6 months, it means 100 is the principal that you borrowed, 20 is the interest that you have to pay as a reward to the lender, the bank, and 120 is the accumulated value. The level of interest rate is dependent on the risk of default of the borrower. If the borrower has lower risk of default, then a lower rate of interest would be charged. If you lend to the government by purchasing treasury bills versus lending to corporate by purchasing corporate bonds, the interest rate will be different because the risk of default of the government is low. Then it means the interest rate from the government would be lower than the interest rate from the corporate bonds. Inflation also affects a rate of interest, with rate of interest expected to be higher in inflationary environment as an allowance for possible depreciation in currency. So when there is inflation, the interest rate will be higher compared to when there is no inflation because of the loss in value of the amount. For example, using the bank, which situations result in a bank being a lender or a borrower? So a lender is someone who lends money or whichever asset and expects to receive interest as a reward, including the capital amount back. And when does the bank lend money? Examples that we have here is when it offers a mortgage to a person wanting to buy a house, when it makes a business loan to a company, and when it buys fixed interest securities. And when does the bank act as a borrower? The bank also borrows money. For example, when it accepts money from savers, when it issues shares to investors, and when it sells fixed interest securities, in those instances, the bank is the borrower. We now move to simple interest. What is simple interest? I just want to also remove this. Okay, interest is credited to an account and it does not earn further interest. That is when we have simple interest, when the interest does not earn further interest. So, yeah, let's start with this. The formula for simple interest is C times 1 plus NI to get the accumulated value, with C being the capital that is initially invested, and then I is the simple interest per annum, and N is the number of years in which the amount is deposited. An investor deposits 10,000 in a bank account that pays simple interest at a rate of 5% per annum. Calculate the accumulated value of the deposit after 3 years. So in this case, 10,000 is the C capital, 5% is the I, and N is 3 years. And using this formula, we know that the accumulated value is equal to C 10,000 times 1 plus n is 3 years, times I is 0.05 or 5%. This is equal to 11,500. So we found the accumulated value based on simple interest. Now we have to move on to compound interest. What happens with compound interest? The difference between simple interest and compound interest is that with simple interest, interest does not earn interest. But with compound interest, the interest itself also earns interest. And the accumulated value from compound interest is C times 1 plus I to the power n, C times 1 plus I to the power n, where C is the capital, I is the interest per annum, and n is the number of years in which the amount is deposited for. So the question is, an investor deposits 10,000 in a bank account that pays, this should be compound interest at a rate of 5% per annum. Calculate the accumulated value of the deposit after 3 years. So 10,000 is the capital, the C, I is 5%, and N is 3 years. The accumulated value then becomes, we say it is C 10,000 times 1 plus I we say it is 5%, to the power 3, which is n. Using your calculator, we can see that this is 11,576.25. That would be your answer using compound interest. And as you can see, from simple interest, we had 11,500 here. But with compound interest, it's 11,576.25. The same term, the same capital amount, the same interest rate. Why is compound interest higher? It's because with compound interest, the interest end also earns interest, making the accumulated value higher. Let's just do a simple example to show the difference between simple and compound interest. An investor deposits 5,000, this is the C, in a savings account that pays 10% interest at the end of each year, this is I. Compare how much the investor would have earned after 6 years, this is N. If the money were invested for 6 years, 1, and 2 invested for 3 years, this is N1, and then invested for a further 3 years, N2. And we've already said that with simple interest, the accumulated value, simple accumulated value, is equal to C times 1 plus Ni. With compound interest, accumulated value is C times 1 plus I to the power n. So for the solution here, to show the difference, we have simple here and then compound here, just so we see the difference. For number 1, using simple interest, we say this is the formula. So the AV will be 5,000 times 1 plus N, it's 6 times I, 10%. And using a calculator, we find that this is equal to 8,000. Then with compound interest, we say this is C 5,000 times 1 plus 10%. This is I using this formula to the power 6. This is equal to what? Using a calculator, we get 8,857.81. Then for number 2, it's invested for 3 years first. So we start with 5,000, the same formula, 1 plus, now it's 3 years, not 6, so it's 3 times 10%. Using a calculator, we get 6,500. Then a further 3 years, the money that would have been gotten is now 6,500 times 1 plus 3 times 10%, which is equal to, using a calculator here, we get 8,450. So this is what we get from simple interest. If you verify this, you see that 8450 is higher than 8000 because here the interest for the 3 years is now earning more interest also, making the amount higher. Then with compound interest, the first 3 years we start with 5000 times 1 plus 10%, the same formula as above, to the power 3. Using a calculator here, we get 6655. Then the next 3 years, we start with 6655 times 1 plus 10%. It's still 3 years to the power 3. This is equal to 8857.81. So this is equal to this. So with compound interest, the accumulated value is the same with or without reinvestment because the interest is already earning interest. And also, as we can see with compound interest, the accumulated value is higher as the interest itself is earning interest. And this can be shown from this graph, whereby with simple interest, the graph increases like this, but with compound, there's an exponential growth because the interest is earning interest, and the accumulated value will be far much higher. Now we move on to the accumulation factor. For time 1, which is less than time 2, we define a T12 to be the accumulation at time T2 of an investment of 1 at time T1. The number T1, T2 is the accumulation factor. Since the accumulation at time T2 of an investment of C at time T1 is by proportion CAT1 T2. So what we are saying is if you start with an amount of C and it increases by a factor of T1, T2 to the accumulated value. This is the accumulation factor, the factor by which this amount C increases by to become the accumulated value. This is the capital, this is the accumulated value. And if you divide both sides by C, we can see that it becomes a T1, T2 is equal to accumulated value over C. So this is how you get the accumulation factor. AN is often used as an abbreviation for the accumulation factor A0 to N. The question to help us understand this, if an investor deposits 10,000, this is C, in a bank account that pays simple interest of 5%, this is I, the interest. After 3 years, this is N. The accumulated value of the deposit becomes 11,500, this is AV. What is the accumulation factor from time 0 to time 3? So we know that A 0 to 3 from this is equal to A3, and from this formula, this is equal to accumulated value, which is 11,500, divided by the capital of 10,000, C, which is 10,000, is equal to 1.15. So the accumulation factor is 1.15. Then to check as a check, we know that with simple interest, accumulated value is equal to C times 1 plus IN, which is equal to, we know C is 10,000 times 1 plus IN or NI, this is 3 times 5%. This using a calculator is 11,500. So this verifies that the accumulation factor is C plus 1 plus NI, because this formula can also be written as AV is equal to CAN, like this. So 1 plus NI is equal to AN. And from equations on simple and compound interest, we know that the accumulated value is C plus NI for simple interest, which means that the accumulation factor A0 to N is 1 plus NI. That's the accumulation factor. And for compound interest, this is the formula, C factor of 1 plus I to the power N, which means this is the accumulation factor, 1 plus I to the power of N. Let's just do a question that would help us understand this. An investment of 1,000 accumulates to 2,500 after 5 years. So 1,000 is the capital, 2,500 is the accumulated value, in 5 years is N. Calculate the accumulation factor A is 0 to 5. So we'll start with 1. A is 0 to 5. This is equal to, we have already said that this is equal to accumulated value over C from before. So accumulated value is 2,500 over C, which is 1,000. This becomes 2.5. So this is your answer for 1. Then 2A, calculate the simple annual interest rate that would give the accumulation factor in 1. And we've already said from above here, A 0 to 5 is 1 plus NI. So here we know that A 0 to 5 is equal to 1 plus NI. And A 0 to 5 is 2.5 from here is equal to 1 plus N is 5 years, 5I, which implies that we move this 1 to this side, it changes sign to negative. So it becomes 2.5 minus 1 is equal to 5I. Then divide both sides by 5. This becomes I. I is equal to 2.5 minus 1 over 5, which is equal to 30%. Then B with compound interest. For compound interest, we know that the accumulation factor is 1 plus I to the power of N. So here it becomes A 0 to 5 is equal to 1 plus I to the power N. And A 0 to 5 from above, we know is 2.5 is equal to 1 plus I to the power N, which is 5. Sorry. N is 5. This is 5 years. So what do we do here? We divide both sides, the powers, by 1 over 5. So this becomes to the power of 1, and this becomes 2.5 to the power 1 over 5 is equal to 1 plus I. And we move this 1 to this side, it changes sign. It becomes I is equal to 2.5 to the power 1 over 5 minus 1. Using a calculator, we see that 2.5 to the power 1 over 5 minus 1 is 20.1%. So we've managed to verify this. We've calculated the simple interest rate of 30% and a compound interest rate of 20.1%. Any questions? We now move to the principle of consistency. What's the principle of consistency? So we let time 0 is less than or equal to time 1 is less than or equal to time 2, and consider investment of 1 at time t0. The proceeds at time t2 will be a t0 t2 if 1 invests from time t0 for time t2 minus t1 t0, or a t0 to 1, a t1 to 2 if 1 invests at time t0 for time t1 to t minus t0, and then at time t1 reinvest the proceeds for time t2 minus t1. If in a consistent market, these proceeds should not depend on the course of action taken by the investor. Accordingly, we say that under the principle of consistency, a t0 to tn is equal to a t0 to t1 times a t1 to t2 up to a tn minus 1 to tn. And just to do this on a timeline, this is 0, this is t1, this is t2, this is tn minus 1, this is tn. What we are saying is this AE T0 to Tn is equal to, if you move like this, step by step, where here we have AE T0 to T1, here it's AE T1 to T2, up to AE Tn minus 1 to Tn. So they just should be consistency, and this in the accumulations, that is, it's continuous to make them equal. And let's do this question. 4,600 is invested at time 0, and the proceeds at time 10 are 8,200. Calculate A710 if A09 is 1.8, A24 is 1.1, A27 is 1.32, and A49 is 1.45. So we will first of all do our number line. Let me just do it on top here so that we have adequate space for the calculation. We start at 0. From here, the times that we have from 0 is it's time 2. Then the next one is 4. Then we have 7, 9, and 10. And from time 0 to time 10, this is this. T0 to T10. And here, if we are going to do it step by step, we know that we want to find AE7 to 10 here. This is the missing item. And to get here, we start from where, then step back from 7, going backwards from the numbers that we have here. The accumulation factors that we have 2 to 7. So we can find this 2 to 7, which is 1.32. And we do not have a 0 to 2. This is also missing. Then we have a 0 to 9. Sorry. 0 to 9 like this, which is 1.8. From 9 going backwards, we have a 4 to 9. A 4 to 9, which is 1.45. Then from 4 going backwards, we have a 4 to 2 here, 2 to 4, sorry, which is 1.1. But just like above, we also do not have a 0 to 2. And we can see that from a 0 to 10, we have two unknowns, a 0 to 2 and 7 to 10. But for a 0 to 9, we only have one unknown, a 0 to 2. So we can use the principle of consistency for a 0 to 9 to get a 0 to 2. We'll start with that. We say a 0 to 9 is equal to a 0 to 2 times a 2 to 4 times a 4 to 9, which is equal to a 0 to 9. We know this is 1.8, is equal to a 0 to 2 times a 2 to 4, we know is 1.1, times a 4 to 9 is 1.45. Then divide both sides by 1.1 times 1.45. 1.1 times 1.45. These will cancel each other. This side we are left with a 0 to 2. So if we say a 0 to 2, use a calculator to calculate 1.8 divided by 1.1 by 1.45. We get a 0 to 2 is 1.1285. So this is 1.1285. And from this statement here, we can calculate A 0 to 10. 0 to 10. From our initial formulas, we know that A 0 to 10 is equal to the accumulated value at time 10 over the capital at time 0. And we have the accumulated value of 8,200 divided by 4,600. This is the capital at time 0. How much is this? Using a calculator, this is 1.7826. So we now have this 1.7826. So for A 0 to 10, the only missing item is now 7 to 10. So using the principle of consistency, we know that A 0 to 10 is equal to A 0 to 2 times A 2 to 4 times A. Sorry. Here it's not correct. We said A 0 to 2 here, and then times A 2 to 7, and then 7 to 10. 2 to 7 times A 7 to 10. And like this. So A 0 to 10, we found it here. This is 1.7826 is equal to A 0 to 2. We found it here. 1.1285 times A 2 to 7. We have it here. 1.32, 1.32 times A 7 to 10. Then divide both sides by 1.1285 times 1.32, 1.1285 times 1.32. These will cancel each other. This is 1, this is 1. So that right hand side, we move it to the left. It's now A 7 to 10 is equal to 1.7826 over 1.1285 by 1.32, which is using a calculator. We find that A 7 to 10 is 1.1967. So we've computed A 7 to 10. Now we move on to present values. We've talked about discounted values. Sorry, we've talked about accumulated values where we're using simple interest and compound interest to determine the accumulated value. So the accumulated value is the amount in the future that you get when you invest a certain amount, is the capital at this time, it is particular interest. Then the present value is like the opposite. It is the amount that needs to be invested now to provide a stated amount of payments later. For example, you want to get 5,000 in 5 years, and you know that you want it after 5 years. You know that the interest rate that you are going to earn from initial capital is maybe 5%. What you want to determine is how much should you invest now for you to get that 5,000 in the future. So the discounted present value at time n is equal to C divided by 1 plus I to the power n, where C is the payment required in the future, I is the interest rate, and n is the time at which payment is required. And we can define V to be 1 over 1 plus I, which gets the present value formula, which is C over 1 plus I to the power n is equal to C times 1 over 1 plus I to the power n. And knowing that V is 1 over 1 plus I, this becomes CV to the power n, like this. That's the discounted present value formula. So let's now do a question. An investor must make a payment of 5,000 in 5 years' time. So C is 5,000 and N is 5. The investor wishes to make a provision for this payment by investing in single sum now in a deposit account that pays 10% per annum compound interest. So I is 10%. Calculate the initial investment required to meet the payment of 5,000 in 5 years. So first to calculate from principle, and then next to calculate using the formula and tables from the institute. The institute issues out formula and tables which can be used in an exam. It contains some formulas and it has a formula that can be useful here. So solution 1 here, we've said that PV is equal to C over 1 plus I to the power n, and in this case C is 5,000 divided by 1 plus 10% to the power of 5, which makes present value is equal to 3,104.61. Then using the tables, in the tables we have the values of fees. So we start with the formula that is PV is equal to CV to the power n, and in this case we know C is 5,000 times V to the power 5, that's 5 years. Let me just show you the tables so that you can see the page. Should be page 162. Of the formula in tables. You should familiarize yourself with the tables. So you see on page 162 here of the tables, we have the compound interest factors at a 10% interest rate. We can find them here. And here the 5 v to the power n here, n being 5, the value is 0.6. The value here is 0.62092. From the tables, we found that V is equal to V to the power 5, that is 0.62092. So this 5,000 times 0.62092 is equal to 3104.61. And as you can see, the answer is the same. The only difference is using the tables, it's much faster because V to the power 5, you get it from the tables instead of trying to use the calculator to input all this 1 plus 10 to the power 10% to the power 5. So that is how you use the tables. Then we move on to simple discount. So just like simple interest, interest does not earn interest. And the formula for the present value using simple discount, it's C times 1 minus ND, where C is the amount to be invested now, that's the capital, N is the time of investment, and D is the simple discount rate per annum. And this is quite simple. We just say calculate the present value of 10,000 due at time 3 years using a simple discount rate of 5% per annum. So the solution present value, our formula says you first say C from here. C is 10,000 times 1 minus our N is 3 years. 3 times I, 5%, 0.05, that is 5%. This becomes 8,500. So that's the present value using simple discount. Then another question is an 8-month loan is repayable by a single investment of 100,000. If the loan is issued at a rate of commercial discount of 15% per annum, calculate how much is initially lent to the borrower. So N is 8 months, capital is 100,000, and the discount rate is 15%. So the present value is equal to C, 100,000, times 1 minus N. It's 8 months, so we have to convert it to years. To convert months to years, we divide by 12. times the discount rate 15%. And from the calculator, 100,000 times 1 minus 8 over 12 by 15% is 90,000. This is how easy it is. Then we move on to compound discount. Compound discount. Suppose an amount C is due after n years and at a rate of compound discount of D per annum. Then the sum of money required to be invested now to accumulate to C after n years is C times 1 minus D to the power n. C times 1 minus D to the power n. This is the formula for compound discount. And C is the capital to be invested now, n is the time it will be invested for, and D is the compound discount rate. Calculate the present value of 10,000 due at time 3 years using a compound discount rate of 5% per annum. It means C is 10,000, N is 3 years, and D is 5%. We just have to input it in this formula. PV is equal to 10,000, which is C, times 1 minus D, or 5%, to the power 3, which is N. From my calculator, I get 8573.75. That would be your answer. Then discount factors. Vn, let's see. Vn is the present value of a payment of 1 due a time n. That is, Vn is the discount factor, just like how An is the accumulation factor. If you remember, when we were talking about An earlier on, we were saying that An is the accumulation factor, the factor by which we accumulate an amount now with to arrive at an accumulated value. And Vn is just the opposite, that is the discount factor, the factor by which you discount the future payment with to arrive at a future value. And Vn is equal to 1 over An. So from the formula above, we know that PV, the formula here, PV is equal to C times 1 minus D to the power n. We got C times 1 minus D to the power C times 1 minus D to the power n. So it means the discount factor, the factor by which we discount C to arrive at the present value, is 1 minus D to the power n, which brings us to this. Vn is equal to 1 minus D to the power n, our discount factor. And using compound interest, we already know that An is equal to 1 plus I to the power n. So if Vn is equal to 1 over An, it implies that Vn is equal to 1 over An, it's 1 plus I to the power n, which is equal to Vn. If you remember, we've talked about Vn being 1 over 1 plus I to the power n. So Vn is just the discounting factor. And also we can use the compound discount rate to determine the accumulation factor, the opposite, like this. An is equal to 1 over Vn. And we know that 1 over Vn, we've already verified that Vn is equal to 1 minus D to the power n. So here we have 1 minus D to the power n. This is equal to 1 minus D to the power negative n, that is An. Since this is in the denominator, it then becomes 1 minus D to the power negative n. That's An. So these are our two formulas. Effective rates of interest. Effective rate of interest over time is the amount of interest a single initial investment will earn at the end of the time period, expressed as a proportion of the initial investment. So denoting the effective rate of interest during the nth period we have AN is equal to, so the effective rate of interest, we are denoting it by IN subscript N. We have AN, which is the accumulated value, is equal to 1 plus IN times AN minus 1. What we are just saying here is to get the accumulated value at time n, we multiply the value at time n minus 1 by 1 plus in being the effective rate of interest during the nth period. So we can rearrange this by dividing both sides by an minus 1. You divide this by an minus 1, an minus 1, this by an minus 1. This will cancel each other out. We then have 1 plus in is equal to an over an minus 1. And then, which implies that if you move 1 to the other side, it's now in is equal to an over an minus 1 minus 1. What we can then do is for 1, we have this an minus 1. 1 is equal to an minus 1 over an minus 1. This is just 1. So we can then have a common denominator that can be shared by the two sides. Comes in is equal to an, this is an minus n minus 1 over an minus 1. That is, the interest that is earned in the nth time period is just equal to the accumulated value at time n minus the accumulated value at time n minus 1 divided by the accumulated value at time n minus 1. That is an. And if an is equal to 1 plus I to the power n, and an minus 1 is 1 plus I to the power n minus 1. If you want to input this into this formula which we have here, those are the values for compound interest. Substituting, what do we have? In is equal to, we said it's an 1 plus I to the power n minus n minus 1, 1 plus I to the power n minus 1 all over 1 plus I to the power n minus 1. This is equal to 1 plus I to the power n. We want to split this. Since the denominator is similar, it's easy. We just have them separately with the same denominator to the power n minus 1 over 1 plus I to the power n minus 1. This will cancel each other out. This becomes 1. And here, 1 plus I to the power n divided by 1 plus I to the power n minus 1 is the same as saying 1 plus I to the power n minus 1. N minus n is 0. This becomes 1 because negative by negative is 1. So this becomes 1 plus I minus 1. Sorry, it's minus 1. Because this becomes 1 plus I, which is the sum amount in this. And then this minus 1, this is 1. If you say 1 minus 1 is 0, so substituting, we find that in under compound interest rate is equal to I, because these two cancel each other out. That is how you prove that IN is equal to I. And therefore, effective rate of interest is the compound rate of interest. Now, let's do this question. An investor's bank balance at various times is as follows. 1 January 2017, 3,000. 1 July 2017, 3,100. And 1 January 2018, 3,300. Calculate the effective 6-month rate between 1 January 2017 and 1 July 2017. There is 6 months between these two periods, so it's a 6 months rate. And then annual rate between 1 January 2017 and 1 January 2018, this is a year. So we'll start with 1. From before, we had said that IN is equal to A n minus A n minus 1 over A n minus 1. So in simple terms, this is the effective interest rate is equal to the value at time n, the value at n minus the value at n minus 1 divided by the value at n minus 1. So here for 1, we can get I by saying the value at time n, which is the last period at time 1 July 2017, is 3,100 minus the value at time n minus 1, which is 1 January 2017, 3,000 divided by 3,000. This, using a calculator, we get 3.33% per 6 months. That's the effective 6-month interest rate. Then for 2, we want the annual one. The value at 1 January 2018, we know that this is 3,300 minus the value at 1 January 2017, 3,000 divided by 3,000 using this same formula. This becomes 10% per annum. That's the annual effective rate. So we are now almost done with this chapter. The effective rate of discount over a given time period is the amount of interest a single initial investment will earn at the start of the time period, expressed as a proportion of the final amount. So DN is different from IN. For DN, is the amount that would be earned at the start of the time period, and for AN it was at the beginning of the time period. It was at the end of the time period, sorry. So DN, that's the formula for DN. And how do we prove that the effective rate of discount is equal to compound rate of discount, like how we did with the effective rate of interest and the compound rate of interest? From our initial computations, we had said that AN is equal to 1 over Vn, which is equal to 1 over 1 minus d to the power n. If you remember all from our initial computations, so 1 over 1 minus d to the power n is just equal to 1 minus d to the power negative n. That would be our AN here. We found the A in terms of D, it's 1 minus D to the power negative n. Then AN minus 1. This is equal to 1 over V n minus 1, which is equal to 1 over 1 minus D to the power n minus 1, which is equal to 1 minus D to the power negative n minus 1. So we now have a n and a n minus 1. Inputting this into this formula, here we get dn is equal to an, this is an 1 minus d, the power negative n, minus an minus 1, this 1 minus d, power negative n minus 1 divided by 1 minus d to the power negative n, because we are dividing by an. That's where the difference is between in and dn. With in, we're dividing by an minus 1, but with dn, we're dividing by an. So it becomes this. And just like what we did with in, we split this. This is 1 minus d to the power negative n, or 1 minus d to the power negative n, minus 1 minus d to the power negative n minus 1 over 1 minus d to the power negative n. And this is this becomes 1. And here, if you subtract the powers, minus n minus 1 plus n, this becomes 1 from this one, minus 1 minus d from this. This 2 becomes 1 minus d. This is equal to d, because these ones cancel each other, and then negative and negative becomes d. So this is a proof that dn is equal to d. The effective rate of discount is equal to compound rate of discount. So thank you. This brings us to the end of the chapter.